Got another question on the electrode potentials topic, and as always the link to the questions in the description of the video if you wanted to try it first. Okay, so the definition of the term standard electrode potential, it's the voltage or EMF of a half cell when measured against the standard hydrogen electrode, and the standard conditions 298 Kelvin, 100 kilopascals, and solutions at 1 mole per decimeter cubed. Standard cell potential is just the most positive minus the least, so we get 1.25 volts. The equation for when the cell discharges or operates, we just need to look at the electrode potentials. So you can see this one's the more positive one, so this half equation is going to run in the forwards direction, which means this one's going to go in reverse. All we need to do is get the electrons to be the same on each side, so we need to double the nickel half equation and add it to the cadmium one. So you can see we get that equation there. Obviously the hydroxide ions cancel because you've got the same on each side of the equation. Next part, what's been oxidized, what's been reduced. So you can see cadmium starting out in oxidation state 0 and it's going to +2, so that's been oxidized. So that means the nickel's been reduced, so it's starting out at +3 in this compound here, just explain that. So oxygen's -2, hydroxide's -1, so you've got -3, so that must be +3. It's going to +2 because obviously 2 hydroxides, 1 minus each. Part D now, so what are the reactions that take place when the recharging process is happening? So you basically want the reverse of the natural reactions of the cell. So remember we said before, because this is more positive, this is going to run, when the cell operates, it's going to run left to right. When you're recharging it, it's going to go that way. So we get this equation here. Likewise, when the cell operates, this top one moves from right to left. So when you're recharging it, it's going to go from left to right. So it's that one there. Now the final part of the question I thought was pretty nasty, to be honest. It's worth more than 2 marks I reckon, but anyway, I'll try and explain it as best I can. So the hydroxide ions decompose into oxygen and hydrogen. I'm going to start explaining the formation of oxygen. So you'll notice I've just written up hydroxide going to oxygen, and I've got some oxidation numbers. So oxygen's obviously -2 in the hydroxide ion, and it goes to 0 in the element. So you can see you've obviously got 2 oxygen atoms there, starting out at -2, going to 0. So 2 oxygens must have increased their oxidation number by 2. So that's a total change of 4. So 4 electrons must be involved in this decomposition process. Because this is an increase in oxidation number, it's obviously an oxidation process, the electrons are going to go on the right hand side. Next thing I'm going to do is get the charges to balance. So I've got 4 minus on the right, I've only got 1 minus on the left, so we'll stick a 4 in front of that. And the final thing I need to do is just get the atoms to balance now. So to get 4 hydrogens on the right hand side, I just need to bring 2 H2O molecules in, and that will also sort out the O's as well. So moving on to the other half equation now. So I think this is the trickier one of the two. So my starting point is hydroxide ions going to hydrogen. Oxidation number of hydrogen starts at a +1, and each hydrogen in the H2 molecule is at 0. So that means we need 2 hydroxide ions, and each hydrogen in there is going to gain an electron, so 2 electrons gained altogether. So we've now got a 4 minus charge on the left, we've got no charge at all on the right, so if I put 4 hydroxide ions on the right, obviously we're going to have to cancel down now, so they're going to disappear, and that's going to go to 2. So in terms of atoms, I've got no atoms left on the left, and I've got 4 hydrogens on the right and 2 oxygens. So if I put 2 H2Os in there, that should sort it out.